Okay, so now we're working on the parallel example of RL, and this is where we have our branch 1 as our resistor branch, branch 2 as our inductor branch, and in this example we're looking at a total impedance that's a parallel impedance, so we have to make sure we don't approach this by simply adding the impedances together like we did in series. That's really important. A lot of times students just want to jump right into an impedance triangle here to solve for total impedance, and that cannot be done, because in doing so, if you were to jump right into an impedance triangle and use that to determine total impedance, you'd be telling me that two 10 ohm resistors connected in parallel equal 20 ohms of opposition, which we all know isn't right. So just remember that it has to be determined through the use of dividing your current into your applied voltage to give you total impedance, or by using product over sum. So let's start by taking a look here, and we'll use the first line of the table again, and that would mean that our resistor R1 would be 10 ohms in that branch. And remember, we calculated a value of 37.7 ohms for our XL value for this inductor. So I'm going to put 37.7 ohms in here in the table. So when we look at the rectangular value of impedance here, it's not something that we can just get directly by putting the two values together as a rectangular value. What we have to do is, again, we could use product over sum here. So we can say that Z total is equal to 10 ohms multiplied by plus J 37.7 ohms over 10 ohms plus J 37.7 ohms. That's going to give us product over sum. So I'm just going to put that in my calculator. All right, so when you're putting in your calculator, don't forget to use your brackets accordingly. So 10 ohms as a real value multiplied by J 37.7 ohms divided by 10 ohms plus J 37.7. Okay, then you hit your result and you can get the value in either rectangular or polar. So right now I've got my calculator in polar mode, so it's giving me a total impedance here that's equal to 9.67 ohms, and we'll get our angle of impedance. Our angle of impedance is 14.9 degrees. For all intents and purposes, you can make that 15 degrees, but I'll put it in at 14.9 degrees. If I'm looking at my rectangular mode to express that, it's going to be 9.34 plus J 2.5 ohms. Okay, so now what we're going to do is put that in our table. So you've got rectangular of 9.34 plus J 2.5 ohms, and your polar value we said was 9.67 ohms at 14.9 degrees. Okay, so notice how again we have a positive angle of impedance, and that angle of impedance is then telling us, once we divide that into our applied voltage, our current will be lagging the applied voltage by that amount. So we're expecting 15 degrees in this case, right? Now, if you look at what that looks like as an impedance triangle, we can draw an impedance triangle now. So in drawing an impedance triangle, we have to use the values that we calculated. So our plus J component here was Okay, so our plus J component here was 2.5 ohms, and our real component was 9.34 ohms. We know based on our polar conversion that that total impedance was 9.67 ohms, and this angle in here of the angle of impedance is, let's just call it 15 degrees. So yeah, we can draw an impedance triangle, but the impedance triangle is really saying what is the equivalent resistance, or I shouldn't say resistance, what's the equivalent impedance as if it was series. So if you think about two resistors in parallel of 10 ohms each, we know that their equivalent series resistance is R equivalent equals 5 ohms. Well, it's the same idea when you draw an impedance triangle for a parallel circuit. Is what you've said is this is the equivalent series impedance. So the equivalent series impedance, if you connected a 9.34 ohm resistor R in series with a inductor that gave you 2.5 ohms of opposition, you would end up with an impedance equal to what we see here, or the equivalent impedance. Okay, so let's come up with our total current here then. So we know that I total is going to equal E source at 0 degrees divided by our impedance, which is 9.67 ohms at 14.9 degrees. Now, sorry, I'm just going to go back up here and put this in at 120 volts at 0 degrees. Okay, so then if we do that, we get 120 divided by 9.67. That gives us 12.4. So that's 12.4 amps. And that 12.4 amps is going to be at an angle of minus 14.9 degrees. And again, we know that if we've done everything correctly, Eli should apply here, indicating that the current is lagging the voltage. And sure enough, we can see that is our I total value here. And our reference voltage of 120 at 0, we've got an I that's lagging by 14.9 degrees. So we can put that in here. 12.4 amps at an angle of minus 14.9 degrees, we can say in there. Okay, so now let's go to multisim. Okay, so here we go with our currents in multisim. So notice how we have total current here is XMM1. We've got that 12.4 amps that we calculated. And in our branch 1, of course, you can clearly see with 10 ohms and 120 volts applied that we're going to have 12 amps of resistor current here in branch 1. And then our 100 millihenry coil has 3.2 amps essentially. And remember, that's a result of 120 volts being connected across what is the equivalent of 37.7 ohms of reactance. So if you calculate that, you'd get 3.2 amps. Now, remember, these two currents are not in phase. So we're going to find that we have an angular relationship between those two currents. And of course, that angular relationship is going to be a 90-degree relationship. So we would have the current of IR at 0 degrees. We would have the current of IL at minus 90 degrees. And then the result would be the total current that is the hypotenuse of that triangle. And we're going to demonstrate that here back at the on the calculations here right now. Okay, so now we're back to to where we're going to look at proving Kirchhoff's current law, which we know means that if we're going to prove Kirchhoff's current law for this circuit, we're going to have I total is got to equal IR plus IL. So if we're looking at our IR value, you know that we said that our IR value is going to be at 0 degrees. And if we take our value of 10 ohms and we divide it into 120 volts, we know that's going to give us 12 amps. So we've got 12 amps for IR. If we look at actually solving this with a current triangle, then our IL value, now I know this isn't to scale, I could probably have made this a little bit more to scale. Maybe I'll do that. So let's just get rid of that, come back, make this a little bit more to scale. So let's go with 3.2 amps here of IL. Okay. Now you may say, how come I'm all of a sudden putting a minus J component in here to my inductor current? Well, the thing is, we need to understand that the IL value is going to be the conjugate of the actual XL value. So when it comes to the XL value being plus J and the voltage being plus J, that's because we take our XL and we multiply it by a value of current to giving us VL. So plus J is going to be maintained in that calculation. Here, if we're dividing a plus J value into a voltage value to give us that branch current, we know that this is going to be E source divided by XL to give us IL, right? So IL is going to equal E source divided by XL. And remember, XL is at a 90 degrees. So when we divide it into our E source at 0 degrees, we know we're going to have a minus J component to that XL. So that means that the total or hypotenuse here is our I total, right? So I total then would be the hypotenuse here. And this angle here we know is indicating minus 14.9 degrees. So let's just come up with our I total as a rectangular and polar value. So I total then is going to be 12 amps minus J 3.2 amps as a rectangular value. For the polar value, we got that already, 12.4 amps at an angle of minus 14.9 degrees. Okay, so this is proving Kirchhoff's current law, and the way we can just verify that is by doing that rectangular polar conversion. So I'm going to put in 12 minus J 3.2 equals, and then I'll convert that to polar, and I get 12.4 at minus 14.9 degrees. So okay, this is where I've connected an oscilloscope so we can look at the phase angles of each one of these branches. And as you know, being a resistive branch for branch 1, that will be a current that's in phase with the applied voltage because it's a resistive branch and purely resistive. We know that voltage and current are in phase when it comes to resistance. So if I was to put the channel B of the oscilloscope across here, we know that that would be the voltage would be representing the same phase as the current, and we would no doubt see a 0 degree phase angle between the applied voltage and that branch. But what I wanted to do was look at this last branch, of which we know should be a 90 degree phase angle, and it should be one where the current is lagging the applied voltage by 90 degrees, and we know that Eli is the acronym that reminds us of that the current will lag the voltage by 90 degrees for a purely inductive branch. Now, in this branch, of course, what I had to do was add a resistance in series, and a very, very small resistance. So notice how I put a 1 micro ohm resistor in series here, because the voltage across it is going to allow me to represent the phase of current, or the angle of the current through this branch. So that's what I did. Now, if you bring the actual oscilloscope display in here, notice how you've got the blue sine wave as the applied voltage, and the red sine wave is going to be that branch current, that last branch, the inductor branch. And we know that that should be a lagging current, so we can see it's clearly lagging here. And I've used the time markers in order to indicate the time delay between the two. Now notice that's a 4.166 millisecond, and if you use that to determine the angular delay, then it would be 4.166 divided by 16.67, which is our period in milliseconds for a 60 hertz wave. And then you're going to multiply that by 360 degrees, and you're going to get 89.9 degrees. So a 90-degree phase shift for that current. So that resistor, by the way, is something we call a sampling resistor, and we use it with oscilloscopes quite often because they can't measure current. They're voltmeters that are connected in parallel. So in order to measure current in any branch, we can just use something called a sampling resistor, and it's got to be a very, very low resistance with respect to the load it's connected to. So we know this inductor has a reactance of 37.7 ohms. We put in a very small value in series in order to represent its current. Okay, last thing here is I just wanted to demonstrate how the use of a current triangle for a parallel circuit can be used to determine the circuit phase angle, or to display the circuit phase angle. And then for a series circuit, of which we just looked at previous to this, the voltage triangle can be used to demonstrate the circuit phase angle. So let's just take a look at that current triangle once again. And remember, we had an IR value at 0 degrees, right? We had a IL value at as a minus J component, and that was 3.2 amps, and IR was 12 amps. We know the hypotenuse then is the hypotenuse of this triangle of 12.4 amps. This angle here is minus 14.9 degrees. Now, how do we know that's the circuit phase angle? Well, really, remember the circuit phase angle is the angle between E source and I total. So if you want to orientate your ES in here, remember it's going to be the applied voltage is going to be right in phase with your IR. So that means that if we were just to look here at E source and its location, we know it would line up directly with our IR value. Now remember, of course, since this is parallel, ES equals VR equals VL. All of those voltages are in phase because it's a parallel connection. So that means then if you're using your source voltage as a reference, what are you going to see? You're going to see an I total value that's lagging by 14.9 degrees here, and that means your theta, or circuit phase angle, is 14.9 degrees, and you could call it lagging ES, 14.9 degrees lagging VS. Okay, I just wanted to kind of demonstrate how the current triangle can be used to display a circuit phase angle, knowing that you can use it to orientate your source voltage, and then from there you know you're looking at the